Introducing endangered birds to Ulva Island, New Zealand. Modeling exponential and logistic growth of the yellowhead population. Because populations are numbers, we can model them mathematically. Given information about birth and death rates, we can predict the future size of a population. Experimental growth occurs when resources like food are unlimited, and logistic growth occurs if there is a carrying capacity that limits the population. Modeling populations with mathematics enables us to predict what a population will do in the future and also points out the concept of exponential growth. Any species that is capable of reproducing more than one individual per adult is capable of exponential population growth. However, exponential growth is rarely seen because most populations are already at their carrying capacity, the maximum number of individuals that an environment will support. One instance in which a species can demonstrate exponential growth is when a few species are introduced to a new environment. This has happened in New Zealand with endangered species. Birds in New Zealand evolved with no land predators, and consequently have no defenses against nest predation. Europeans introduced weasels, possums, domestic cats, and rats that decimated many bird populations on the main island, but many smaller islands remain predator-free. Consequently, a strategy for preserving endangered birds is to relocate populations to remote islands. Hence, the relocation of yellowheads to Ulva. In this model, we predict what will happen to this population. The question: as this population increases, when will it reach its maximum population? In 2001, 27 yellowheads were relocated to Ulva Island. Rats had been eradicated and other predators never existed on the island. We will assume that yellowheads have exclusive territories that are 0.1 hectares. The island is 267 hectares. We want to know when they will cover the island. When will the yellowhead population reach the maximum? To answer this problem, we will need two things. 1. What is the maximum population? And 2. How fast will the population grow? You are going to perform two tasks. Task 1. If the island is 267 hectares and each bird needs 0.1 hectare, what is the maximum population? A hectare is 100 meters by 100 meters. Task 2. What can cause the population to grow or decrease? Growth due to birth or immigration. Decrease due to death or emigration. Because yellowheads do not fly over water, we will just consider birth and death rates, usually combined into a reproductive rate. R by R equals B minus D. The exponential growth model is dn over dt equals r times n, where r equals the reproductive rate, n equals the number of population, and dn over dt is the change in the population per unit time. When will the yellowhead reach the maximum? Set up a spreadsheet that looks like the one here. Use the formulas that you can find on the previous slides. If you are unsure as to how to calculate these formulas within Excel, you can do them by hand. In this example, assume that the birth rate is 1.5 per individual in the population. 3 birds survive from each nest tended by 2 adults, and the death rate is 1. These rates are per year. Now graph the results and examine the graph. Use an XY scatter graph so that each value is tied to a year. Look at this graph of exponential growth. and answer the following questions. 1. How would you describe a curve like this? It curves, but how? 2. When is growth rate the fastest? 3. When is it the slowest? And 4. What is the difference between the growth rate in 2003 and 2008? Note that you can get these answers by estimating from the graph or from reading values on the spreadsheet. Therefore, if you are having difficulty calculating the data or graphing the line in Excel, look at this slide. And finally, when will the yellowhead population reach the maximum? Look back at slide 4 if you forgot what you calculated for the maximum. Is the exponential growth model realistic? Our exponential growth model suggests that the population overshoots the maximum. What happens after that? If you expanded the model to more years, what would happen? A better model might predict that as the population approaches carrying capacity, the growth would slow down. As birds become more crowded, there may be less food or nesting sites. The logistic equation is I equals N times R times K minus N all over K. Look carefully at what we added. We added K minus N all over K. What happens to this quantity when N is very low, 0 or almost 0? What is the effect on I? What happens when N is at or very close to K? What is the effect on I? Convert the exponential formula to the logistic formula in your spreadsheet. The logistic growth model is more realistic, right? Although we still are not considering factors such as fluctuating food supplies, changes in weather, disease, competing species. However, we can do analyses and numerical experiments. Look at the graph or the spreadsheet. Answer the following questions. 1. When is the growth rate the greatest? 2. How do you identify this on the graph? 3. Why is growth rate low at the beginning? 4. Why is the growth rate low near the end? 5. What do you think would happen if you extended the model out to 2050? Complete the quiz within your packet. Which of these graphs is 1. Shows linear growth, 2. Shows logistic growth, 3. Shows exponential growth, 4. None of the above. 5. In each of the diagrams above, describe where the greatest rate of change occurs. Which of the following is 6. A line graph, 7. An XY scatter graph, 8. A column graph, or 9. A pie graph?